Welcome to this presentation. My name is Yahong Liu, a principal scientist from IMEC, Netherlands. My talk today will be about miniature wireless transceiver design for minimally invasive implants. So before my talk, I would like to give a short introduction about myself. I received my PhD from National Taiwan University 2009. Then in 2010, I started joining IMEC, the Netherlands. The current position is principal member of technical staff, working on ultra-low power wireless technology for Internet of Things and health applications. I received consolidator grant from European Research Council regarding to a project of Internet of Neurons from 2021 to 2026. The project is about developing a minimally invasive wireless interfacing for intra-cortical brain-computer interface. I'm also serving as technical program committee for IEEE ICC and RFIC Symposium since 2016. So here is the outline of this talk. First, I will give an introduction about minimally invasive insertable and injectable implants, including several application examples. Second, I will cover several signal propagation modalities that can be applied inside the body. The third part, I will talk about the design considerations of insertable transceivers and especially focus on few big components like antenna, crystal, and also power source. Then I will specifically focus on a case study with high bandwidth and miniature transceiver for brain-computer interfaces. And at the end, I will conclude my presentation. Okay, first I would like to give an introduction. In this slide, I would like to compare the wearable and implantable sensors. So for wearable sensors, they are non-invasive, lower cost because you don't need the surgery. Sometimes the sensing quality may be limited, for example, due to the skin contact condition. And another side is the implantable. Implantable need a surgical procedure, so they are invasive. You may have a complication of infection, foreign body reaction, and of course also surgical risk, because a large battery need to be placing. They are not comfortable. The surgical procedure and maintenance cost is also higher. And finally, implantable sensing typically provides better sensing qualities compared to wearable. So there is a trade-off, clear trade-off between these two: invasiveness, cost, and also the sensing stimulation quality. There's a trend moving forward is that can we have an implants that is minimally invasive? So we have to go through a minimally invasive surgery. Such surgical procedure is performed through a tiny incision hole instead of a large opening. This will lead to much quicker recovery, less pain, and also less complication. And that is typically we call insertable implants. Here, I would like to show one example with insertable cardiac monitor. And figure shown here is a ICM from Medtronic called Review Link. So the purpose is that it will be placed beneath the skin and then continuously monitor the cardiac activities and also at the same time transmit out the data. Compared to the wearable cardiac monitor, this insertable cardiac monitor provides much stable sensing quality. And you can see the size is much smaller, in the order of 3 millimeter times a 44 millimeter scale. And they are using minimally invasive procedure by open a small hole of 5 millimeter incision to push in these insertable sensors. Finally, you can see there they have wireless connectivity. They continue to send out data. One key thing is that the battery power is limited, so the power consumption of the such device has to be optimized. Here, I would like to discuss a bit more about minimally invasive surgery. Here, I would like to use 2 examples. One is based on insertable based on endoscopy, and another one is injectable based on syringe. So endoscopy is a long, thin, and flexible tube that has a light source and camera at one end. Usually you can use endoscopy to do many things. One thing, for example, is perform imaging. Second is that you can also use that to sample the tissue, or even you can use that to perform surgery. We call keyhole surgery. So implant is put inside this body through a small keyhole, cut on the skin, and this endoscopy tube is inserted to perform surgery with a very small invasiveness. So on the right side, I would like to show you this injectable with syringe. Is even smaller scale than endoscopy. The implantable syringe is suitable for placement of a rod-shaped type of implants with a diameter around millimeter. So the implant is inserted through a kind of needle to subcutaneous tissue. One example is this very cheap RFID system. Once you inject it to the human's arm, for example, they can be used to access the building or even financial transaction. And of course, many pads also have such kind of insertable RFID. Okay, now in the following slide, I would like to give several application examples. So first, I would like to start with the sense and diagnosis of gastrointestinal tract. So endoscopy is most conventional way of diagnosing the GI infection or any other GI gastrointestinal disorders. And as mentioned previously, the endoscope is a long tube that has a light source and camera at one end, and doctor can see the image from the other end. And the key limitations of the endoscopy is that they need to perform by a professional personnel in a professional place, for example, hospital with doctors. So their cost is usually very high, and they are not meant for so-called transient diagnosis, meaning that you can do it for longer period of time. Typically, such endoscopy check is just in few minutes. So recently, we have a development of home-based wireless ingestible sensors for GI diagnosis. We call this is a wireless capsule endoscopy. The first capsule endoscopy was approved by FDA in early 2000. So what it does is that it takes a picture and send the picture continuously in real time via a wireless channel. And the patient will wear a belt, and it will real time receive the picture sending out from the capsule. after 8 to 10 hours, the pill will automatically drain out by the human body. The benefit is that the patient does not need to go to the hospital. They can do this at home, and the diagnosis can be longer than just a few minutes. The difficulty is that the size of the pill is typically large, and it's quite difficult to swallow. Sometimes there's a risk of stuck in the GI tract. And it's also very difficult to control the location of the pill because it will continuously flow through your GI tract. And they cannot stay inside the body at a specific location for longer than 8 to 10 hours, unless you have a constipation. So in ICC 2020, we present a insertable GI sensors. The idea is that the small pills, the capsule, is inserted via the endoscopy biopsy channels, and they will be attached on the surface of the digestive tract, for example, your stomach, and then they will stay there for a longer period of time. By doing this, we are able to diagnose at a specific location of the digestive tract for much longer time. And after a certain period of time, for example, a few days, they can be self-detached and then drained by the body automatically. The most challenging part is that such capsule or pills has to be extremely miniaturized, because the largest biopsy channel of the endoscopy is typically roughly in the range of 3 to 4 millimeter, and this put a lot of design challenge on this wireless pills itself. So the next example is the neurosensing of the brain. So neurosensing can be optical, electrical, or even acoustic. But so far, electrical neurosensing still provide the best temporal resolution. And for neurosensing in the brain, we want to sense the activity of single neuron. So the spatial resolution is also very important. There are different methods that can be used to do neurosensing in the brain. So they have a different level of invasiveness. Of course, they're related to how large is the scale should be open in order to place such a neurosensor. So the first one will be a very common one, is a wearable EEG. They are non-invasive, but they have a very poor spatial resolution because they are sensing millions of neurons together. We also have ECOG electro array. They are more invasive because you need to open a pretty large area of the skull. Yet still, they are not providing very good spatial resolution because they are sensing hundreds to thousands of neurons. Finally, is the multi-electro array that is placed below the skull, directly inserted into the cortex. The invasiveness is depending on how large is this microelectro array. They can be made very small, such that we don't need to open a large area of the skull. They can provide very good spatial resolution down to just few neurons. Next, application example, not only for sensing but also stimulation. They have a similar property. So the conventional wearable or surface muscle stimulation, sometimes we also call functional electrostimulation. They are attached on the skin. They need large stimulation amplitude because such that they can penetrate through the skin to the muscle. So patient can clearly feel it's very uncomfortable, and they are not meant to long-term use. Also, they are not precise because you cannot really stimulate exactly nerve you want to target. There is also so on the other side, we also have a more newer development with the injectable muscle stimulator, or we call biome. In such injectable muscle stimulator, since they are right next to the muscle or the nerve, you don't need very high stimulation amplitude. You can already stimulate the muscle. They are very precise because we are placing right next to the nerve we want to stimulate. Okay, so next I would like to talk about several modalities for the embodied signal propagation. In this slide, first, we would like to introduce the channel property of the tissue. Tissue is actually composed of the cells, many cells with membrane. When we apply electrical signal, the high frequency signal tends to directly pass through the membrane that leads to higher conductivity. While the low frequency signal tend to circulate around the membrane, leading to lower conductivity. And we can use such circuit model to understand the behavior, the characteristic of the tissue in terms of frequency response. There is also so-called Coco dielectric model to model the dielectric property across a frequency. There are three dispersion areas: alpha, beta, and gamma. Most of the time, we will be operating close to beta dispersion in this frequency range. On the right side shows the data that is provided from the literature from the group of Gabriel. They perform the dielectric measurements of multiple tissue across very wide frequency range from tens of kilohertz up to 10 gigahertz. You can see that especially the dielectric property including permittivity and also conductivity. And when the frequency goes beyond 1 gigahertz, the conductivity will quickly increase. This also indicates that for the signal propagation, it's better to operate below 1 gigahertz, such that we can have a sufficient low attenuation. The propagation can also in either near field or far field region. The definition of far field or near field is typically determined by the wavelength of the signal, the distance between transmitter and receiver, and also the size of radiation source. For near field, for example, inductive coupling, capacitive coupling, or galvanic coupling. And they typically operate in a region where the distance between transmitter and receiver are relatively shorter than the wavelengths. It's also possible somewhere between near field and far field that we call midfield. So in the case, for example, EM or ultrasound can operate in such region. Finally, the far field, when the distance between the transmitter and receiver is much larger than the wavelengths and also the size of the antenna, then they are mainly in the far field region. Then that, for example, can include like EM radiation, optical, or sometimes ultrasound. So the first propagation method I would like to introduce is a near-field capacitive and galvanic coupling. So there are mainly two types. Capacitive coupling is assuming that the electrical field is returning to the external ground, while the galvanic has close electrical fields that is both electrical field is all within the tissue. We can also understand from the Maxwell equation, when you apply electrical field, you will create ionic current, or sometimes we call it electrolytic current, and then this leads to the signal propagation. Most of the prior art focus on on-body communication, meaning both of the transmitter and receiver are placed on the skin. And then they are typically operate at a relatively low frequency below 10 megahertz that leads to limited bandwidth. And since such propagation methods are near field, they don't need antenna, that also shows that they are more suitable for miniature implants. So here I would like to show you a few examples use capacitive and galvanic coupling in implantable communication. So on the left, you can see the wireless capsule endoscopy use capacitive coupling. Thus, the ingested pills inside the digestive tract, sending the signal via the tissue and to be received by the external receiver attached on the body. On the right side, we can see the wireless intra-cardiac communication using galvanic coupling. And several implants are placed in different parts of the heart, and they need to communicate with each other. So their approach is that they use differential electrode and then they propagate signal through the tissues, the conductivity of the tissues. So here, I would like to, second one I would like to show you is the near-field inductive coupling. This is the most commonly used propagation approach for implants because it can simultaneously provide the power and also the signal for communication. We can try to understand this from Maxwell equation. So assuming we excite with a time variant current source, then this will convert into time variant magnetic field, and then it will couple from the primary coil to the secondary coil. And in the secondary coil, the changing of the magnetic field will introduce electrical field, and this electrical field will be sensed by this rectifier. And they are typically operate at the lower frequency because that leads to lower attenuation. Since it's also mostly magnetic induction, it's also better for the tissue heating, which I will discuss a bit later. This type of inductive propagation require resonation to increase the quality factor such that they can get good coupling efficiency. Because of that, that is also the reason such kind of inductive coupling cannot achieve a wide signal bandwidth. Worth to mention is that such kind of propagation or communication can be done by modulating the amplitude that is coupled from one end to another end with ASK modulation. And it's even possible we can do reverse link from secondary to primary with load shifting by changing the impedance on the secondary coil part. Such propagation is quite sensitive to the misalignment. especially when the coil size is reduced. And this is significantly degrading the coupling efficiency. That is one issue need to be overcome. The coil size and distance can dramatically influence the coupling efficiency. The rule of thumb is typically assuming that the diameter of the coil is larger than the distance between two coils. So in this slide, I would like to talk about the far field EM radiation. So we can start with, again, the Maxwell equation. If we have a time variant current source as excited here, it will produce a time variant magnetic field. This time variant magnetic field will induce time variant electrical field. If the antenna has a size, has a length of half lambda, half wavelength, then they will fulfill this propagation condition, and then you will radiate the EM wave with a wave equation shown here. So as you can see, the speed of light is a constant, which is a frequency multiplied frequency multiplied wavelength. And if we want to have a smaller antenna, we have to increase the frequency. However, when we increase the frequency, the attenuation inside the tissue will also increase. So there's a fundamental trade-off between size and attenuation. The bandwidth of EM radiation is typically wider because we are operate at a higher frequency. And the implantable antenna also typically has less directivity. This means that it has a less issue with misalignment, which is suitable for deeper implant. Next, I would like to discuss if we further expand the spectrum, light can also be used for in-body propagation. This figure shows the penetration depth of the light or EM radiation wave versus different wavelengths or different frequency. And you can see the light in the visible light or infrared can actually has a pretty deep penetration depth. The blue curve is the absorption from the water, and the red curve is the mere scattering model. And also observe from this figure, it's clear that visible light or near infrared light can be used in propagation, but in this region, the scattering is actually much worse than absorption. This is the last propagation method I will introduce. It's based on the ultrasound wave propagation. Here, I would like to use an example with a music system using a speaker. So if we vibrate the speaker membrane, then it will produce acoustic wave. It will compress or expand the air media. And the wavelength will be determined by how fast we vibrate the speaker. We can also extend this to ultrasound by using the ultrasound transducer to produce acoustic wave. This kind of ultrasound transducer can be implemented with PZT, PMOD, or CMOD. Let's also take a look at the wave equation. You can find this in many textbooks from ultrasound propagation. And you can also see that it's similar to the wave equation of EM radiation. If we just replace this P pressure by electrical field, then it's the same as the equation that we showed before for EM radiation. We can also calculate
the speed of sound by using this equation. So kappa is the stiffness of the tissue and rho is the density. When you calculate this, when you calculate the wavelengths, you will find that inside the tissue, typical tissue, it will be roughly around millimeter scale. So this make ultrasound very suitable for insert application with millimeter scale. It also has an advantage that it does not attenuate as much compared to EM radiation because it's inside the tissue. The sound wave does not attenuate. The downside is that depending on the stiffness, the propagation will have a reflection. For example, if the acoustic wave propagates between soft tissue and bones, then there will be a strong reflection between these interfaces. Finally, because ultrasound typically operate at few hundred kilohertz to megahertz, they typically have a limited transmission bandwidth.
Okay, in this slide, I would like to have a very high-level comparison between different modalities. And here again, I separate into near-field propagation and far-field propagation. And we are looking at from different aspects. The first aspect is that the tissue loss and scattering. This will lead to power efficiency, low power efficiency, and also potential heating issue. And EM wave and optical has worse propagation property than typically inductive and acoustic at a lower frequency. And for the interface reflection, again, inductive has a better reflection than acoustic. And for the sensitivity to the misalignment, typically for the near field is worse than the far field, except for the optical case. And for the bandwidth, EM propagation and also optical potentially has higher bandwidth. In terms of size, the galvanic or capacitive coupling, acoustic can achieve the smallest dimension. So the next part will be related to the design consideration of the insertable transceivers. We will first discuss what is the biggest area or volume consuming building blocks, and then we will discuss them separately, and at the end we also want to discuss the potential tissue heating issue. So currently wearable system demands already miniaturized electronics. You can imagine watch, earbuds, patch. The future insertable, implantable electronics will further demand a 10 times volume reduction, especially on the width because of the insertion requirements. Then such miniaturization will also demand even lower power consumption from the electronics. So the insertable sensor or stimulation system composed of mainly 4 key components. The first component is sensors or stimulators. This could be electrical or non-electrical sensors, stimulators. We also have a signal processing. For example, processing a signal such that we can relax the communication requirements. We also have a power source, for example, battery or energy harvester. Finally, is the wireless communication to transmit the data or receive the data between the implant and external device. And quite often, this wireless communication module occupies a large portion of the system volume.
So in this slide, let's take a look at one example of teardown of a wireless ingestible image sensor. So in this device, you can see several components dominate the system volume. First, sensors. In this case, it's image sensors. Also need to have a LED. We will not focus on the sensor part. The next part is the wireless communication. So for wireless communication, you can see antenna occupies large volume, crystal as well. Finally, it's a power source. In this case, it's a battery, but sometimes can also be wireless power transfer using energy harvester. So in the following slide, I would like to focus on these few big components: antenna, crystal, and also the power source. So let's start with the antenna. So the loss inside the body increase significantly when the frequency is above 1 GHz, as we already introduced in the previous section. That is why sub-gigahertz frequency is preferred for the implantable radio. And one very popular frequency choice is 400 MHz. And we can calculate the 400 MHz half lambda is roughly 37 centimeters in the air. When it is put inside the tissue, the half wavelengths can reduce to roughly 5 centimeters because the permittivity is higher. But if we try to put this antenna into a millimeter scale volume, then this antenna will become like electrical small antenna. The definition of electrically small antenna is the antenna size that is much smaller than lambda over 10. This will lead to high quality factor, as we already introduced, and high quality factor will lead to narrower transmission bandwidth, and also it will be very sensitive to the environment.
In here, I would like to discuss the relation between the quality factor and the size. The definition of quality factor is signal bandwidth divided by the carrier. And from this paper, they have a derivation of the quality factor of antenna versus their dimension. So K is 2 pi over lambda, and A is a radius of antenna. So Ka indicate the ratio between the size and the wavelength. For electrically small antenna, 1 over Ka is typically much smaller than a cubic of 1 over Ka. That means we can, assuming the quality factor is roughly is cubically proportional to the volume. And if we have for example, Ka smaller than 1 over 10.1, then it can easily has a quality factor up to 1000. And in this case, if we have 1 GHz carrier frequency, the bandwidth will be smaller than 1 MHz. Next, we would like to discuss the impedance variation. So as indicated previously, small antenna has high quality factor, and this high quality factor will lead to a high sensitivity to the environment, location, or even the tissue components. So this figure shows the S11 parameter versus different condition. For example, when the antenna, when the battery is placed near the antenna versus there is no battery, you can already see the resonation frequency of the antenna has been shifted. And this frequency shift will be even more obvious when you are placing in different type of tissue. Therefore, a tunable impedance tuning matching network is typically desired in such miniature wireless module. Then I would like to talk about the alignment requirements. Small antenna, if it's from the EM radiation, they typically have a poor directivity, and hence they are not very sensitive to the misalignment. However, for near field type of propagation, for example, inductive coupling that has a millimeter scale coil, or like optical transmitter, then they are very sensitive to misalignment. As shown in the figure here, assuming a inductive coil with a diameter of 10 centimeter, and even you are just shifting 10 millimeters, sorry. If you are just shifting few millimeter away from the center, then you can see the communication bit error rate is already significantly increased. Similarly, also for optical are also very sensitive to misalignment. So next big component is about the frequency reference, typically a crystal. So one question is that can we try to get rid of the crystal? We have to see from two aspects in the wireless communication. First is that the crystal, the carrier frequency error, the impact to the wireless communication. If there's a frequency error, that means the receiver frequency and the transmitter frequency may not be the same. And in this case, we might not be able to correctly receive the signal. We can say maybe we can increase the bandwidth of the receiver such that even there is a frequency error, we can still receive, but then this will also compromise the selectivity of the receiver, which leads to poor interference resilience. The second scenario is timing error. Most of the wireless system is operating under condition of duty cycling, heavy duty cycling to save power consumption. But if there's a timing error, that means that the receiver may not wake up at the right time to receive the transmitted signal. We can, of course, increase the turn-on time of the receiver, but that will lead to also high power consumption. In a wireless communication system, the standards typically define the accuracy should be roughly below 10 ppm error for most of standard. And with such requirements, the on-chip oscillator still cannot meet such a requirement, and we will need crystal. So this slide, I would like to show you the size difference of the crystal and the transceiver. On the left side, you can see the smallest crystal that is available on the market. On the right side is the fully integrated radio transceiver ASIC. In this work, we demonstrate that with the existence of the external hub, we can use a network to calibrate the frequency, and it is possible to achieve the crystal-less operation. And in this design, we don't need a crystal, so the whole radio can be extremely miniaturized, with only antenna and the ASIC, and leads to millimeter scaled volume. Next to the antenna and crystal, power source is the biggest component in the system. As shown in this figure, it shows the the internal resistors, and also the battery capacity versus the volume. So for wearable device, for example, Apple Watch, typically has roughly 1,000 millimeter cubic volume, and they have a roughly few hundred milliamp hour. While for the insertable implants, they only have a few millimeter cubic volume and has a capacity much lower than 1 milliamp hour. At the same time, their internal resistance is typically in the order of tens ohm to hundreds ohm. They indicate if you have a large peak current draining, then this will create very large voltage drop, which increase the burden of power management units. In addition, if the implant has a battery, then automatically they will increase the certification requirements, because battery typically has a chemical component, and this can lead to potential leak. A recharged battery is also having potential heating problem. Instead of using batteries, there are also many miniaturized implants use wireless power transfer as the power source. One example, very popular example, is the cochlear implant, which use inductive power transfer to reduce the size and also the safety. This figure shows the wireless power transfer with different modalities, and they are comparing with different aspects. For example, receiver size, link efficiency, penetration depth. And inductive coupling, inductive power transfer, and acoustic power transfer are very popular. The inductive power transfer, they provide very good power transfer efficiency, and it is also possible to combine the powering and the communication. Recently, ultrasound power transfer is also getting popular because it has an extremely small volume and can penetrate to a deeper tissue depths. In the next two slides, I would like to touch a bit on the topic of tissue heating. When we propagate the signal inside the tissue, there's a potential heating possibility. And the regulations specify specific absorption rate with a unit of watt per kilo in order to quantify the tissue heating, potential tissue heating. And they also indicate a smaller implant will have a higher requirements to meet the SAR regulation. And here I would like to discuss two types of SAR regulation, electrical version and also acoustic version. For electrical SAR requirements, here is the definition. Sigma is the conductivity, and E is the electrical field, and rho is the mass density. So in FDA, they specify it has to be the maximum average for human head exposure to electrical and magnetic field energy should be less than 1.6 watt per kilogram per 1 gram tissue. And for IEEE, it specifies 2 watt per kilogram measure every 10 gram tissue. We can translate into this in a millimeter square to around 0.1 milliwatts. For an acoustic one, it's also well known in many ultrasound applications. The limit is the spatial peak time average intensity limit is 720 milliwatts per centimeter square, which can be translated to 7.2 milliwatts per millimeter square. If we compare the electrical and acoustic, we can see the SAR regulation limited the maximum amount of power that can be propagate inside the tissue, the acoustic apparently has a much higher power that is allowed inside the tissue, which has a low chance to cause the tissue heating. The tissue heating can also be caused by the power consumption of the electronic itself. In Gonzalez's paper, they present simulation results of an ASIC implant placed inside the eye, and they observe temperature rises in different scenarios. And here is their simulation result. It in principle tells us that when the implant is smaller or the power consumption higher, they will lead to higher temperature rise. There is no closed form equation that can predict how small, how large the ASIC need to be, or how low power consumption need to be. But there's a kind of general rule of thumb, design guideline is that every centimeter square of the electronics, the power consumption should be less than 40 milliwatts. So next topic, we would like to discuss the volume and bandwidth trade-off in miniaturized insertable radio. We want to use a case study of high bandwidth and miniaturized transceiver for brain-computer interfaces. Almost 220 million people in Europe suffers from neurological disease, including, for example, stroke, dementia, etc. They are not only those people who are affected, not only lose their quality of life, it's also a huge burden to the society. It is also a substantial life expectancy reduction, and this is going to get worse in the coming decade because of the aging population in Europe. So here I would like to talk about intra-cortical brain-computer interfaces. The intra-cortical brain-computer interfaces help to restore sensor, motor, or even cognitive functions for the patients who suffer from neurological disorders. One famous example is a project called BrainGate from DARPA. In this project, the patient who suffer from neurological disorder and cannot control his arm, and the brain-computer interfaces, the intracortical brain-computer interfaces decode the neural activity from roughly 100 neurons, which allows the patient to be able to regain the control of his arm to perform simple grasping function. Human brain has roughly 80 billion neurons. So one research question is that how much neuron need to be decoded in such brain-computer interfaces? This is a very interesting research questions which has been studied by many neuroscience group in their community. So one study from Stanford University, they estimate the number of neurons need to be decoded is increased exponentially with the test complexity or the dimension, the control dimension. There are also a few examples. As, if we can decode 100 neurons, then we can perform simple grasping. If we are able to, if we want to do further fine limb control, for example, tying the shoelace or even playing piano, then we might need more than 10,000 neuron decoding. And if we want to perform full body movement by controlling the exoskeleton then even more than 100,000 neurons decoding will be needed. Because of this reason, the number of neurons that is recorded simultaneously is continuously increasing in the past decades, as surveyed by Stevenson lab in this plot. You can see roughly every 6.4 years, the number of neurons being recorded is double. And the highest number of neurons that is recorded are implemented by IMAX high-density neural pixels probe. Some people even say this is a Lamborghini in the neuroscience community. However, this kind of high-density neural sensors are usually not wireless because they are usually applied in the small animal like a mouse. But if we want to further apply it to humans, this setup will not be clinical viable. So one question is that what is the requirement if we want to transfer this data wirelessly? Then we have to take a look at the data rate requirements. Here, in this figure, showing the signal characteristic of the neuron firing. In the neural signal, you will have action potential, which is a spike, what we call spike, and they have a high frequency component up to 10 kilohertz. While we also have a local field potential, has a higher dynamic range with a low frequency, but dynamic range is higher. On top of that, we have many other interferers. For example, the effect from the stimulation or the offset introduced from electro tissue interface. And let's do a simple estimation. If we want to transfer the data from 1,000 channels, sensing channels in this setup, and then in order to cover the action potential with 10 kilohertz components, then we need to have a roughly 25 kilohertz sampling rate in the ADC. Furthermore, in order to have sufficient dynamic range in the range of 60 to 80 dB, we will need an ADC with up to 10 bits. If we put it together, then you can see the data rate can go up to 250 megabit per second. And this starts to become a big data problem where we need to optimize between communication and computation. Okay, as explained previously in the previous section, smaller antenna has higher quality factor, which limited bandwidth. So in this survey, we try to put the data rate versus wireless module area in the same plots for several implant devices. You can observe that there's a general trend that when we want to increase the data rate, then the module area will also increase. And you can see that the state-of-the-art commercial off-the-shelf BLE module is roughly a few tens of millimeters squared. If you want to have 100 megabit per second data rate, then the area of the wireless module will immediately go above centimeter squared. On the other hand, we prefer smaller hole opened on the scalp in order to reduce the recovery time and avoid opening large area of the scalp. This figure shows the surgical of the opening scalp hole. We call it craniotomy. In order to minimize the invasiveness, we prefer to open only small burr hole in 1 centimeter or even smaller, below 1 millimeter with a twist drill, which such dimension we are able to help the patient will be able to recover much faster in several weeks or even days. In order to achieve this, then the electronics or the wireless module should have a diameter not larger than 1 centimeter. Let's take a look at what is currently out there. So here shows a few examples with preclinical wireless brain-computer interfaces for either primates or even humans. And you can see all of them are either they need to open pretty large area of the skull if we want to increase the number of sensing channels. And also they are based on head mount head stage, which is fixed on top of the skull. So this type of structure has a risk in infection and also potentially accident that we will hit this head mount stage. So it's very clear that they are not clinical viable due to the large wireless system module. How can we design a minimally invasive wireless brain-computer interfaces? First, we have to have a high-density neural sensor and stimulator with a small form factor such that they can be insertable. Second, we also need to overcome the bandwidth and volume trade-off of the wireless system module. Then, we should also explore the data compression method such that we can minimize the transmission, power consumption, and the requirements. Here I would like to share with you one recent example from Neuralink. Neuralink is a star company from Elon Musk. Last year, they present their new wireless brain-computer interface concept. So in their wireless brain-computer interface, they will open a skull hole with area roughly around a few centimeters square, and then they place a device they call Fitbits on the skull. So such a device has a flexible electrode on one end, and they also have a battery inside, and then also wireless communication. So the flexible electrode is going to be inserted to the brain, and then this device is going to seal or replace the skull hole and then seal them. Because they also have certain data compression method allows them to just transmit with few megabit per second, and they can be achieved with Bluetooth Low Energy. Although it is still a few steps away from the high bandwidth, minimally invasive wireless brain-computer interface, but it's already showing a big progress. Okay, so now I would like to share with you a few prior work in this area. So first I would like to show you a transcutaneous optical link that can potentially tackle bandwidth and volume trade-off. So this figure showing here, the transceiver is placed in between the skull and the skin, and the communication is only across the skin. We call transcutaneous communication. And worth to mention is that typical thickness of the skin on top of the skull is roughly 4 to 5 millimeters for humans. And for such optical communication, they use near infrared based VCSEL, the vertical cavity surface emitting laser, and they can achieve up to 300 megabit per second data rate, and that is exactly what we need for high bandwidth brain-computer interfaces. And also VCSEL is extremely small in the millimeter scale, and also consume low power. The main downside of such approach is that they are extremely sensitive to the misalignment in the range, so the precision has to be in the range of 100 micrometer. This will need a very precise placement in the wearable devices. And furthermore, we want to further move having a communication that can directly send in the data from the cortex to the air, and the optical approach cannot be penetrated through the scalp. That is also another big issue. Next example is based on the gigahertz EM radiation using impulse radio. Impulse radio ultraviolet is so currently one of the most promising methods and also popular wireless communication. So here in the figure, it shows the impulse modulation. So the data is modulated in a very narrow pulse in the range of 100 picosecond to few nanosecond. On top of that, we can also apply biphase shift keying, embedding the data between 0 phase or 180 phases. The frequency band is in the range of 3 to 7 gigahertz in this work, which comply to FCC regulation. In certain region of the other world, for example, in Europe, the frequency will be higher, above from 8 to 10 gigahertz. But either way, such ultra-wideband regulation allows us to have sufficient bandwidth for the brain computer interface application. As already explained in the previous part, large bandwidth require large antenna. So antenna size is roughly in this work is 1 centimeter square. So it still does not fit into our target of millimeter scale for insertable. So inductive coupling is another example, as inductive coupling are frequently used in many implantable applications, although they typically has a limited bandwidth. Different from two examples. This example, their communication is not only across the skin but also across the scalp. So the transmitter is placed on top of the cortex, and then the transmitted signal crosses both scalp and the skin. We call it transcranial communication. And as shown in this figure, they are in this work. They use a pig scalp to mimic the human scalp, because the pig scalp has a thickness of roughly 7 millimeter, which is very similar to human's scalp. As explained in the previous slide, the dimension of the coil, or diameter of the coil, should be larger than the distance between the primary and secondary coil, such that they have a sufficient coupling efficiency. In this work, they have a coil size of 1 centimeter, roughly 1 centimeter square. Such area of coil will increase the quality factor, which potentially will limit the signal bandwidth, and also they will have a higher resonant frequency at 100 megahertz. In this work, they propose to literally DQ, meaning that they reduce the quality factor by inserting the series resistance into the resonator, such that they can achieve a high data rate up to 200 megabit per second. Although this is a very high data rate that can potentially be used for brain-computer interfaces, they are not minimally invasive. Their size is still relatively large. Also, one downside is that since they reduce the quality factor, That means it's also not ideal for such a complication to also accommodate wireless powering. From the few examples showing above, it seems that there is no suitable wireless propagation method that can fit into millimeter scale size, achieving hundreds of megabit per second data rate, and at the same time being able to propagate through the scalp. The key bottleneck is really different layers of the tissues has a different type of propagation property. Especially the scalp is thick and is difficult to propagate through multiple propagation methods. Here I would like to show you two recent work presented in the literature showing a special approach to overcome this. So the first one is in Guinea from University College London. They use approach called they put the sheet across the scalp and then split the inductive limb into two parts. So above the scalp, they have one inductive coupling link that provide the power and data. Also, another inductive link is providing power and data below the scalp to the cortex. Another approach is from Michigan and ETH. They choose multimodality approach. So they use IVE or inductive link to propagate between the scalp and also the skin. And they use near infrared to propagate below the skin to the cortex. So by doing this, they can choose the proper propagation methods at different layers of the tissue. So far, both of these works still demonstrating they are doing the powering and communication with the sub-cubic millimeters cubic neural sensors distributed on the surface of cortex, and their sensing channel is still limited. But their approach demonstrated here provide a possible solution forward to solve the bandwidth and volume trade-off issue in the brain-computer interfaces.
Another direction we can explore is to do data compression. To explain this, I will start from typical neural signal processing. So after we record the data of the neural firing from the neural sensor, we can apply the filtering to remove the noisy part and also suppress the slow time variant signal. And then we extract this action potential, or we call it spike. By extracting the features from this spike waveform, we can do the clustering and then try to recognize from the same channel which neurons are firing the pattern. And we call this a process called spike sorting, because one sensing channel can record the neuron firing from multiple neurons. Regarding to the wireless transmission, of course, we can do full transmission of the raw data. This will lead to very high data rates and also high requirements on the wireless communication. We can also just transmit the spike time by detecting by setting a threshold and then sending out the timestamp of the spike. By doing this, we will also lose the spike feature, and this might be only suitable for certain neuroscience applications. We can also do so-called on-chip spike sorting. We transmit after we sort the spike. First, we have to recognize the spike features from the waveform and then perform on-chip feature extraction and also sorting. By doing this, they will This approach will have a highest computation and storage requirements, but they can help to reduce the communication requirement at the same time, keeping the features of the spike waveform. In any cases, if you ask the doctors or neuroscientists, they still prefer to have a raw data because they want to use that to analyze the neuron firing pattern. Okay, now is the conclusion. So at the beginning, I introduced the insertable implants that can minimize the invasiveness. At the same time, it's also possible to provide better sensing and stimulation qualities compared to the wearables. We also cover the system design of miniaturized wireless transceiver for insertable implants. We especially focus on antenna design, frequency reference, and also the powering source because they occupied the significant portion of the system volume. Finally, I cover a specific design topic related to the wireless communication for intra-cortical brain-computer interfaces. There exists fundamental trade-off between the bandwidth and also volume. This will require new propagation methods to overcome. Thank you very much for joining my presentation, and I'm very happy to answer any